Now, coming to the different other type of hybridization is your nothing but we will see sp3d hybridization. sp3d. So sp3d, what I said, it will be nothing but that is trigonal bipyramidal. Alright, sp3d hybridization. I have said you already, it is trigonal bipyramidal. So which all molecules will be coming under it? It will be PCl5, it will be SbCl5, PF5. Alright, it will be. Alright, these all molecules will come under it. Now here it is not possible to draw the floral diagram because D subshell has got 5 orbitals. We can say that is dx, dxy, dxz, dx square y square, dz square. Got it? So it is not possible to draw what you can say all those orbitals and show it. It becomes possible means it becomes very clumsy. It will become. Got it? It will become very complex. You will not understand anything in the diagram. So we will be drawing here equivalent diagram and we will show you. Got it? Now let us take the example of PCl5 molecule as I said you. So PCl5 phosphorus has got atomic number 15. So it belongs to group 15 also phosphorus. Got it? So if you write the electronic configuration, what you find is that phosphorus 15 is 1s2, 2s2, 2p6, 3s2 and 3p3. Got it? 3s2 and 3p3. Got it? I said you that it is not necessary that all the what you can say it will be it should be unpaired. Paired electrons can also participate in hybridization. How it is? See here. So what will happen is that one electron from the S subshell will go to the D subshells. It will be 3s1 and 3d1. It will be 3s1. One electron will jump from the 3s subshell to the 3d subshell. So what you got it here? So see here 3s1, 3p, you got it 3 unpaired, alright, and 3d, you got this 1 unpaired. So 1, 2, 3, 4, 5. So in this 5, what you can say unpaired electron, 5 chlorine atom will come. Here one chlorine, here one chlorine, here one chlorine, here one chlorine, here one chlorine. So how many chlorine? 1, 2, 3, 4, 5. So hence it is going to form what? PCl5. Why chlorine? Because 17, see atomic number 1s2, 2s2, 2p6, 3s2, 3p5. So chlorine is having deficiency of how many electron? 1 electron. So it is get 1 electron from phosphorus. Here another chlorine will get 1 electron from phosphorus. In this way 5 chlorine atom will undergo bond formation. So here also same thing. Who is undergoing hybridization? Phosphorus molecule, phosphorus atom. So what are the subshells involved in hybridization? 1s, alright, and 3p and 1d. So hence it is what? sp3d. For that reason it is sp3d hybridization. Because 1s you can see here very clearly 1s and 3p subshell is involved and 1d subshell is involved in hybridization. So hence it is sp3d hybridization. Alright. Now next is here we will see what you will see is that what are the subshells. I have already said you that is 3px, 3py, 3pz. Alright. 3s subshell, 3px, 3py, 3pz. You know that you have seen it already in sp2, sp3, sp, you have seen it, that how p subshell we are drawing it. Now here d subshell, which d subshell will undergo hybridization in PCl5 molecule or SbCl5 molecule or PF5 molecule, that is dz square. Why? Because it has got similar energy, almost comparable energy as that of 3px, 3py and 3pz. Understood what I said? Which subshell? That is nothing but which orbital it is? Rather I should say which orbital? It is nothing but 3d. Sorry, I am drawing this. 3d z square is involved in hybridization here. 3d z square. So how do you represent? You represent in this way. You know that. 3d z square. Alright. It is involved in hybridization. So 3d z square. Because here 3d subshell means 3d orbital means which particular orbital is participating in hybridization? We have got 5 orbitals, isn't it? 3d. I said you already. We are having dxy, dyz, dxz, dx square y square, dz square. So which one? This one. Why? The reason is that this particular subshell almost have got similar energies as that of 3px, 3py, 3p, what you can say z as well as 3s. Almost similar, comparable energies. Because they only participate in hybridization. Because whenever the what you can say, redistribution of energies takes place. Almost the difference in energy should be not be so large. It should be little bit, slightly. The difference in energy is going to take place. Alright, so hence this particular subshell is involved. Got it now? So hence what are the orbitals involved here, or what are the subshells here involved? So subshell is 3s subshell and 3p subshell. 3p is 3x. Under 3p subshell we have got 3 orbitals, 3px, 3py, 3pz. Alright, and under 3d subshell, one orbital, that is 3d z square, is participating in hybridization. So here what I said, what are the what we can draw? We cannot draw the floral diagram. So we will be drawing the, what you can say, the equivalent diagram. Equivalent diagram will be drawing it. Let us say PCl5 molecule, we can say that. So this is the this is your axial bond, which is slightly bigger, and these three are the equatorial bonds. These three are the equatorial bonds, we can say that. These three are the equatorial bonds, you have read it already. These three are the equatorial bonds, and this is the axial bond. So this angle is 90 degree and this angle is 120 degree, isn't it? This is 120 degree and this angle is 90 degree. And axial bond, you can see I have done it slightly bigger. Generally, in case of PCl5 molecule, the axial bond length, in case of PCl5 molecule, the axial bond length is 215 picometer and the equatorial bond length is 204 picometer, we can say that's it's slightly bigger. 215 and this is 24 means slightly bigger, we can say that. Why it is slightly bigger? I have said you already in basic theory, once again I am saying you, because this particular atom will suffer repulsion from this two fluorine atom. So as to have minimum repulsion and maximum stability, this bond will be going a little bit outside. So as to have minimum repulsion and maximum stability, this bond will be slightly outside, will be stretched little bit outside. Got it? So that the bond length is slightly bigger for that particular reason. And this is called trigonal. This is trigonal, and these two hands you can see, which is stretched outside, they are called as bipyramidal. So it is trigonal, bipyramidal. This is your PCl5 molecule. Same thing you will see in, this is your sp3d hybridization, we got it. sp3d, I have already said you 1s, 3p and 1d subshell is involved. You can see that. Same thing we can draw it for sp3d2, which will be octahedral in shape. sp3d2. sp3d is trigonal bipyramidal, sp3d2 is octahedral in shape. What are the example we can give it? We can give the example here is SF6. Got it? We can give it SCl6, we can say that. SF6, we can say that. SCF6 also we can say that. Clear? Or we can say TF6 also we can say that. Or TCl6 we can say that. Clear? So it will be octahedral in nature. So here what are the subshells is involved here? Same thing. Here you will find it out. That is nothing but 3s subshell is involved. Then 3p subshell is involved. And 3d subshell is involved. Alright, so let us write the electronic configuration, it will be clear. 16. So 16 means it will be 1s2, 2s2, 2p6, 3s2 and it will be 3p4. See, 6 for 10, 10 to 12 for 16. Alright, so here what you will find, that one electron from the s subshell, alright, one electron from the s subshell and one electron from p subshell will go to the d subshell. So hence it will be what? 3s1, then 3p3 and 3d2. Alright, 3s1, 3p3 and 3d2. So see here, 3s1, this is unpaired, 1 unpaired, 3p3, 3 unpaired, and 3d, here 5 should be there, 5, out of that 2 is unpaired. So what you are getting it here, 1s subshell, 3p subshell and 2d subshell is participating. 1s, 3p and 2d. So hence it is what? sp3d2. For that reason, sp3d2 is involved. Alright. So in this way, what we find is that why the electron will jump, I have already said you, from s subshell to d subshell, from p subshell to d subshell. Why it is going to jump? Because when the fluorine atom will approach, fluorine is 9, 1s2, 2s2, 2p5. Alright. So it is when the fluorine atom is going to approach the sulfur atom. So when the fluorine atom is approaching, absolutely, then the attractive forces is taking place, due to which the energy is released. And this energy helps to jump the, what you can say, this electrons from s subshell to d subshell and p subshell to d subshell. We can say vacant d subshell. Because d subshell is vacant, it will jump for that reason only. and hence you can say that redistribution of energy is going to take place, and hybrid orbitals will develop, and by the hybrid orbitals this sort of hybridization is going to take place. What is that? sp3d2 hybridization. What is the shape? Octahedral in shape. Got it? Clear? In case of SF6 molecule, I have taken the example, or any other molecule can take which is octahedral in shape, is also sp3d2 hybridization. Either the molecule is sp3d2 and octahedral, or we can say that if you know the shape octahedral, then the hybridization will be sp3d2 and the bond angle will be 90 degree. We can say that. Got it? So now what are the subshell involved? I already said you S subshell and 3p subshell. So what are the orbitals in 3p? 3px, 3py and 3pz, and 2d subshell is involved. We can say that. Clear? So here what you find is that is 2d subshell is involved. 2d subshell. Now which are the subshells of 2d is involved here? Already I said you dz square. In the previous example I have said dz square is having similar energies as that of what you can say 3p. Here also another is there, that is dx square y square. Dx square y square. Alright, that particular subshell is involved in hybridization. We can say that dx square y square, the subshell is involved in hybridization. Alright, how is dx square y square? You know that this is your dx square y square. Dx square y square. This one is this subshell, and dz square already we have seen it. So what are the subshell I am saying, dx square y square, that is nothing but orbitals will be involved. So in 2d subshell, dx square y square and dz square will be participating in it, and in 3p subshell all the orbitals 3px, 3py, 3pz will be involved, and s subshell will be involved in hybridization. Why? The reason is same again, because they have got similar energies. Alright, they have got similar energies, we can say that. Clear? So you can see it also that the energies are similar, how it is. Now here it is 3s, isn't it? Clear? It is 3p. Okay, so 3p means L value is how much? 1. So n plus L will be 3 plus 1, 4. Again it is 2d. So SPD. Alright, 0, 1, 2. So L value is here what? 2. So 2 plus 2 it is 4. 3 plus 1 it is 4. Here 3s. 3 it is 1. That is 3 plus 0 it is 3. So almost similar energies are there. For that particular purpose they are involved in hybridization. Got it? Understood? Now we will see that is your diagram. Equivalent diagram. Here also we cannot do the floral diagram, we will see the equivalent diagram. So SF6, how it will be? See here. SF6, 6 fluorine atoms. I'll make this one a little bit bigger so that it will be clear to you. So this is your SF6 molecule, we can say that, which is octahedral in shape, we can say. Clear up? Fine. This is sp3d2 hybridization. Similarly, we have also got that is sp3d3 hybridization. sp3d3. So sp3d3 we can have IF7. IF7. So what you find is that that is atomic number will be quite bigger one. So that is here what you will find is that in case of IF7, now we need to understand that iodine atom has got 7 electrons in the outermost shell. Alright. Now fluorine atom has also got 7 electrons in the outermost shell. Both they require 1 electrons. Alright. Now in iodine, what are the what you can say subshells involved in hybridization? You will find it out. That is, I means it belongs to which period? Let us count it and see. Fluorine is second period, chlorine is third period, bromine is fourth period, iodine is fifth period. That means 5s subshell, 5p subshell and 4d subshell is involved in hybridization. 5s, 5p and 4d subshell is involved in hybridization. So which 5s subshell? One 5s. 5s is only one, isn't it? 5p subshell, how many orbitals? 3 orbitals. 5px, 5py, 5pz. And 5d subshell, which are the 3? Because what I said, sp3d3, isn't it? Clear? In case of iodine, I am drawing only the outermost. I am writing the electronic configuration. That is 5s1, 5px1, 5py1, 5pz1, then 5d, which one? xy. Alright, then 5d xz and 5d yz. Alright, you know, there are 2 in case of d subshell. There are 5 orbitals. Out of that, 3 are planar and 2 are axial. Already I have talked about the 2. Alright, that is dx square y square and dz square. They are axial over. Now, those 2 are having same energies. Now, these 3 are having the same energies because these 3 are planar. We can say that these 3 are planar. We can see. If nothing I am writing, that is also one. Understood. So, in this way, you can see that is 5s, 1s subshell, 3p subshell, and 1, 2, 3, 3p subshell and 3d subshell. So, as a result, what is that? sp3d3 it is involved in hybridization. Alright, this is for the iodine, the last outermost subshell which is participating in hybridization. I am doing it. I did not write the whole atomic number, you know that. I have counted it and I have showed it to you. Similarly, for the fluorine atom also, 7 fluorine atoms will participate because 1, 2, 3, 4, 5, 6, 7. Each iodine will give 1 electron to 1 fluorine and hence 7 fluorine atoms will participate and it will undergo bond formation. Got it? So, what is the shape of sp3d3? It is nothing but pentagonal bipyramidal. I hope you are following it. IF7, it is pentagonal bipyramidal. We can say that. Clear? Bond angle will be, one it will be 90 degree, another will be nothing but 72 degree, so to say. I am tried and showed to you. What are the subshell involved? I have showed you. What are the orbitals involved? I have showed you. Why it is involved? That also I said, because they have got the similar energies, the comparable energies, we can say that. And how it is sp3d3? You count it and see, you will be getting it, or you put it in the formula, you will be getting it. IF7 molecule is put in the formula, you will be getting it. Alright, now let us see the diagram for IF7. What I said, it is nothing but, here it is, you can see I, 1, 2, 3, 4, 5, 6 and 7. These are longer, these are little bit longer stretched. The reason is the same as I have given in PCl5, because all these are the equatorial bonds and this is the axial bond. These two are the axial bond, which is slightly bigger than the equatorial bond. The reason is the same, because it will suffer more repulsion from these two fluorine atom. So as to have less repulsion and maximum stability, it is little bit outside. So you can see this pentagonal, this diagram you can see this pentagonal. I am just, this is not required, no? This is not the actual bond. So I am making a dotted line, this one. I am rubbing it means I am making it as a dotted line. Dotted line means which is not required. Alright, so you can see that. So hence it is pentagonal bipyramidal, we can say that. The molecule is pentagonal bipyramidal. In this way, IF7. Clear? So, now the last one in hybridization we will come to is DsP2 hybridization. So basically, if you see the number, the value of X, for sp3 also it is 4 and for DsP2 is also 4. But DsP2 is a special case, exceptional case, we can say that. I have said you, there are many exceptional. Chemistry is full of exception, definitely, you know that. So in this way, you will find those molecules which are charged species like NiCN4 2-. Generally, you will be studying this one in class 12 also. A chapter will come coordination compounds. So the example which I am going to give it to you now, they are the coordination compounds. Alright. So what is that? NiCN4 2-. We can say that. Or CuCN4 2-. Nickel tetracyanide. Here copper tetracyanide. Iron. Of course it is iron. We can say that. Clear? So basically that is the DsP2 hybridization. Listen carefully, is being shown by those species which are charged. You can say that, not neutral species. Neutral species will show sp3 type of hybridization. Already we have discussed with you. Neutral species will generally show, and charged species will generally show, that is DsP2 kind of hybridization. So to say, we can say that. But the condition is that in those atom will what you can say show DsP2 hybridization which is having d subshell present in it. Suppose charged species is there but it does not have a d subshell, means the atom, the atomic number is not such that it is having a d subshell, then how it will show the DsP2 hybridization? Are you getting me point? My point. Here's nickel, the atomic number is 28. Copper, the atomic number is 29. So when you write the atomic number 28 and 29, you will see d subshell is coming here in it. Suppose you will take a molecule, alright, like oxygen, is having d subshell? No. Then how it will show? That is DsP2 hybridization. So use the common sense. Use the common sense. You will come to know the answer. Alright. So hence those molecule only will show which contains at least a d subshell, or at least it should have a vacant d subshell. Then also it is being present. That means elements belonging from third period onwards can show what you can say dsp2 kind of hybridization. But it should be charged. Again I am saying it should be charged species, because you can see I have given the two examples there. You can have any other examples. Many other examples you can have it. So, but it should be charged species. Now, how will you draw it? Got it. Now, before what you can say going here, I have to calculate the oxidation number of this central atom. This is on a central metal atom. I said, you know, this particular examples again I will teach you in class 12. A chapter will come, coordination compound. There I am going to teach you again. I am going to tell you again about it. And this is known as ligands. This is called as CN is a ligand. What I said, ligand, L-I-G-A-N-D. What are ligands? Ligands are the donor atoms. It will donate to whom? It will donate to the central metal atom. Why? Because central metal atom, you will write the electronic configuration and see it is having deficiency of electrons. Alright, for that reason, it donates electrons to the central metal atom. Which is central metal atom? This one is a central metal atom. Metal, no? This is metal atom, central metal atom. It is going to donate electrons to, what is that? Nothing but to the nickel, to the copper, we can say that. Who is going to donate? Cn is going to donate. So hence Cn is called as ligands. Ligands means donor atoms, which donates electrons to the central metal atom. So what I said, donates electrons. So how many electrons it is donating? At least one pair. That is, it donates lone pair of electrons. Hence what I told the name of the chapter to you, coordination compounds. Means it forms coordinate bonds with the central metal atom. Cn forms coordinate bond with central metal atom. Cn forms coordinate bond with nickel atom. Alright, coordinate bond, which is noted by an arrow. You have read it already. Alright, so hence it is said to be S. Alright, now let us see the formation. So I have to first find the oxidation number. So you know that how to find the oxidation number. Take it as X. Cn, the valence is -1. How many Cn is there? 4 Cn. So it will be -4. And the total charge of the species is -2. C is equal to -2. Total charge is -2. So how much you got? X is equal to nothing but, this side will go, it is +4, -2 it is nothing but +2. So oxidation number of nickel is +2. We find the oxidation number in this way only. The one which you do not know, you will take it as X. Fine. Then after that, this is 1 Cn, the valency is -1. Or oxidation number is -1, we can say that. So 4 Cn, so X minus 4 is equal to -2, so X is equal to +2. So you got it, the oxidation number of nickel is +2. That means in +2 oxidation state, nickel reacts with cyanide ion. Got it? Undergoes hybridization or bond formation in cyanide ion to form NiCN4 2- species. We can say that. Clear? Now, nickel atomic number I said you, that is 28. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. See, it's 28. But I have nothing to do with nickel. I have to do with Ni2+. So Ni2+, how it will be formed? 1s2, 2s2, 2p6, 3s2, 3p6. Outermost shell is this. See, highest principal quantum number 4. This is outermost. This is not the outermost. Even if it comes last, but it is not the outermost. I have taught you already. So it is from here 2 electrons will be lost. From here 4s. Because highest principal quantum number determines outermost shell. So this is the outermost shell. So 2 electrons will be lost from here. Alright, see carefully, understand it carefully, recapitulate, which I have taught you in atomic structure. So it will be 3d8. Alright, so hence what you find is that, what you are getting it, you draw the spin quantum number, you will find it out. That vacant orbital sum is there, 1, 2, 3, 4, one more I want it, here 5. Alright, so a little bit bigger, let me make it this one. Done. So, and 4s also it is vacant. 4s is vacant because 2 electrons is lost, it is vacant. Now 3d8, this is 3d8, 1, 2, 3, 4, 5, 6, 7, 8. Alright, so now not only it contains, that is this unpaired electrons, and here that is vacant orbitals. Also, definitely you know that along with 4s, 4p subshell is also there, na? Which is also vacant. 4p is there, na? Of course 4p is not involved here in bond formation, but that does not mean it is not there. In the fourth cell, 4s is also there, 4p is also there, 4d is also there. But I don't want 4d here. I want up to 4p only. Alright? Why? Why I want up to 4p? Because I want how many? 4 vacant orbitals I want. Why 4? Because how many ligands are there? 4 ligands. Each ligand will give how many pair of electrons? 2. Because what I said, ligands are donor atoms. What it donates? It donates lone pair of electrons to the central metal atom. Lone pair means 2 electrons it will donate. So hence how many unpaired, what you can say, vacant orbitals I want? Vacant orbitals, how many I want? 4. Why it is 4? See here, 4 ligands are there, 4 ligands are there. Each will give 2 electrons to the vacant orbital, isn't it? Now you cannot have here 1 electron, so 2 more electron will come here. You know that it's not possible. Alright, each orbital can accommodate maximum 2 electrons of opposite spin. So hence, what will happen? Now you will study there in class 12 that Cn is a ligand and it's a very strong ligand. So as it is strong ligand, as I said, this is an exceptional compound. As a strong ligand, it will go against the Hund's rule. It will go against the Hund's rule and the pairing is going to take place. See, this electron will come here. Generally, electron jumps from lower to higher, but here it will go against the Hund's rule because it's a strong ligand. Strong ligand, what it will do? Pairing. It will do the pairing. Automatically, it will do the pairing. The pairing is going to take place and the 4 vacant orbitals are created. 1, 2, 3 and 4. Got it now? What I said? This is a strong ligand Cn. How will you know strong ligand and weak ligand? You will study everything there. Alright, but here just I am saying you for your knowledge, it is a strong ligand. So strong ligand, what it will do? It will go against the Hund's rule and it will pair up the unpaired electrons. Listen carefully. It is going to pair up the unpaired electrons. Alright, so 2 unpaired electrons is there, the pairing is going to take place. Why it is going to do? So as to create a vacant orbital. So in the vacant orbital, 2 electron can be donated. See here, I have donated 2 electrons to each. So I have donated one to D subshell, another to S subshell, another to 2p subshell. So what are the orbitals involved here? See here, what are the orbitals involved here? S, then it is 2p and it is nothing but 2d. Alright. That is, sorry, what I wrote, I am very sorry. This is your D subshell and here it is 1S and one it is 2P. I am very sorry. This is your 3D subshell, this is, isn't it? This is your 3D, this is 4S and 4P. So 1D subshell, 1S subshell and 2P subshell. So it is nothing but DSP2 for that reason. The hybridization is very simple. DSP2. Alright, that's one thing you need to remember, that is strong ligand, pairing is going to take place. Alright, it is go against the Hund's rule because already I said this is an exceptional compound. Alright, so now if it is DSP2, what is the shape I said? Square planar. So how that I will be drawing it? Ni, then square planar. The shape is this: 1 Cn here, 1 Cn here, 1 Cn here, 1 Cn here. This is, I will write it here 2 minus. So NiCN4 2 minus. This is shape. It is square planar. What I said? Square planar, P-L-A-N-A-R, planar, square planar molecule. Understood? First I wrote the nickel configuration, then I wrote Ni2 plus. Why? Because oxidation number I got it as 2. So hence I created the orbitals here. Alright, I want 4 vacant orbitals because 4 ligands are there. So it will going to donate. See, so 4 vacant orbitals is created. Now what are the orbitals? DSP2, 1D, 1S and 2P. Alright, so hence it is called DSP2 hybridization, which is square planar in nature. This is all about your, we can say, hybridization. Thank you.